students. So in this 10th lecture, metric space 10, we are going to study complete metric space. Complete metric space and its examples. Complete metric space. Now, you know metric space. So what do you mean by complete metric space? If we consider some Cauchy sequence in this metric space, and if this Cauchy sequence is convergent, then we say that this metric space is complete metric space. Whenever we have to show any metric space is complete, then we have to consider one Cauchy sequence and we have to show that it is convergent. Then that metric space will be complete metric space. So let us define it. So metric space XD is said to be complete. It's said to be complete if every Cauchy sequence in it converges to a point in capital X. Every Cauchy sequence, if it converges to a point in that metric space, then it is said to be the complete metric space. So let us prove some examples of this complete metric space. So example number 1. So here let this C of closed interval 0, 1. You know, whenever we conduct first article, at that time we have studied that C of closed interval 0, 1 means it denotes that the set of all bounded continuous real valued functions defined on closed interval 0, 1. So let C of closed interval 0, 1 be space of continuous real valued bounded functions defined on closed interval 0, 1, and metric D is given by D of Fg, that is equal to this maximum of mod f of x minus g of x, where this 0 less than or equal to x less than or equal to 1. Then we have to prove that this C of closed interval 0, 1 is complete metric space. Now here 0 less than or equal to 1, it means that is this x belongs to this closed interval 0, 1. So to prove that this C of closed interval 0, 1 is complete metric space, we have to consider one Cauchy sequence. We have to consider one Cauchy sequence in this metric space. So let Fn be a Cauchy sequence. Let Fn be a Cauchy sequence in the C of closed interval 0, 1. And let this epsilon greater than 0 be given. Now as we are assuming that it is Cauchy sequence, so therefore by definition there must exist a positive integer n0 such that this D of Fm is less than epsilon for all this Nm greater than or equal to n0. Now in this example, what is metric D of Fg? That is maximum of mod f of x minus g of x, where x belongs to closed interval 0. So here also, what does this imply? This implies that maximum of mod Fn of x minus Fm of x, where this x belongs to closed interval 0, 1, it is less than epsilon for all this Nm greater than or equal to N0. Now what is this? This is the Cauchy criteria of uniform convergence. This is the Cauchy criteria of uniform convergence. So let F be the limit of uniformly convergent sequence of continuous functions. Sequence of continuous functions, and itself is continuous, on closed interval 0, 1. So this implies that the Cauchy sequence which we have considered is continuous on this closed interval 0, 1, and therefore it is complete matrix space. Now there is another example. So let L infinity, this is the symbol, L infinity be the set of all bounded numerical sequences xn in which metric D is given by this d of xy is equal to the supremum of mod xn minus yn this over n, where this x is equal to sequence xn, y is equal to sequence yn, and this all belongs to this L infinity. So here we have to show that it is complete matrix space. So again we have to consider one Cauchy sequence. So let xn be a Cauchy sequence in L infinity, and let xn is equal to ain. This is the one symbol ain, where I is equal to 1, 2, 3 ... Now this L infinity is bounded. L infinity is bounded means there exists this capital M greater than 0 such that this mod ain is less than or equal to m for I is equal to this 1, 2, 3 up to n. Mod ain less than or equal to m. Now as we are assuming that this xn is a Cauchy sequence, therefore again by definition of Cauchy sequence, for epsilon greater than 0 there exists n0 such that this d of xn xm is less than epsilon for all nm greater than or equal to ng. Now in this example, what is d of xy? D of xy is supremum of mod xn minus y. So here this implies that this is supremum of mod xn minus xm over n is less than epsilon, which implies that supremum of mod xn means that is ain minus aim, it is less than epsilon, and for all this nm greater than or equal to n0, this is our argument number 1. This is our argument over m. This is our argument number 1. And which implies that as this supremum is less than epsilon, it means which implies that mod ain minus aim, this must be less than epsilon. must be less than epsilon. Or take number 1. Instead of this, we will take this. This is our argument number 1. And for this I is equal to 1, 2, 3 up to dot dot dot. Now let I be fixed. Let I be fixed. Then what will happen? If we take I fixed, then by this inequality implies that AI1, AI2, AIN is a Cauchy sequence, and it converges to AI, and this converges to AI. Now taking limit of 1 as this m tends to infinity, we have mod AIN minus AI, it is less than epsilon, for all n greater than or equal to infinity. So finally we have mod AI, this can be written as mod AIN minus AI plus AI, and here we can use the triangle inequality. So by triangle inequality, it is less than or equal to mod AIN minus AI plus mod AIN. So it is less than, this is epsilon and this is plus. It means this AIM is bounded. It means this AI is bounded, and therefore it converges to that L infinity, and therefore it is complete metric space. So these are the two important examples of this complete metric space. So we stop here.